Water has been one of our main sources of power and energy for centuries. This beautiful old water mill in Saugus, Massachusetts is the birthplace of the mighty steel industry in the United States and was hailed as the best in the world in 1650. By our modern standards, it was highly inefficient, since all the power had to be used directly at the source. Bad summer droughts and severe winter ice jams paralyzed the water wheels for weeks. Invention of the steam engine and electricity resulted in the vast power distribution systems of today, which, ironically, still depend to an important extent on water as a source of energy. The rapid growth of our modern civilization and its industrial might has created a thirst for energy beyond man's wildest dreams. Hundreds of new generating plants and transmission networks are being built to serve rapidly growing communities. Although some emphasis today is on the development of nuclear power, the supply of thorium and uranium deposits is limited and still uneconomical as a source of energy in most areas. With the continued depletion of fossil fuels and the limitation of nuclear fuels, it is essential that we investigate every possible power source to feed the giant networks that carry the very lifeblood of our modern civilization. Yes, eventually we must find a source of unlimited power. And even in this atomic age with development of power from nuclear sources, our attention is once again turned to water. This time to a source of energy that man has thus far failed to harness to generate electricity, the mighty ocean tides. The highest tides in the world are found at the head of the Bay of Fundy in Canada, and where the tides are highest, the potential power source is greatest. For 40 years, engineers have been intrigued with the problem of harnessing this vast source of power that is unaffected by droughts, ice jams, and silting that decrease the power output of our modern river hydroelectric plants. In the early 1920s, Dexter P. Cooper made the first large-scale study of tidal power production in this area. Cooper, however, lost support during the financial crisis of 1929, and his plans were never realized. From 1935 to 1937, the United States Army Corps of Engineers actually started to build a one-pool tidal power project limited to the Cobscook Bay area. They completed construction of 3 small tidal dams before the project was discontinued in 1937. Tidal power is by no means a 20th century idea. For hundreds of years, man has made puny efforts to use tidal power. Small tidal mills in England and Western European countries were used to grind corn in the 11th century. This spice mill in Massachusetts developed about 50 horsepower from a single tidal pool. 4 large water wheels located under the building used the power created by trapping water at high tide and releasing it at low tide. In the operation of any single pool tidal power plan, power generation is not continuous because the power head is too small while the pool is filling. Furthermore, the operation of any single pool tidal project is complicated by the fact that high tides occur 50 minutes later each day. In 1956, the governments of Canada and the United States directed the International Joint Commission to investigate the engineering and economic feasibility of harnessing the tides of Passamaquoddy and Cobscook Bays between New Brunswick and Maine. For this purpose, the Commission set up the International Passamaquoddy Engineering Board and the International Passamaquoddy Fisheries Board. Individual committees composed of the best engineering and scientific brains on tidal power studies from both nations were gathered to study the intricate aspects of this gigantic investigation. This launched one of the most exhaustive studies of tidal power in history on an international scale. A field office and soils laboratory located in Eastport, Maine, started the detailed surveys, tidal observations, and subsurface explorations necessary to determine the best layout and design of the project. At high tide, the waterfront at Eastport looks exactly like any other small New England seaport. The water laps close up under the buildings and piers. Ferries arrive from Canada and discharge their passengers. The fishing fleet ties up here at Wordsworth Dock, and to a stranger, everything looks normal. No one would suspect the complete metamorphosis that takes place at low tide. The full impact of the enormous tidal range in this area is now evident. A 26-foot drop at extreme low tide lays the whole waterfront bare. 140 billion cubic feet of water flow through this area every 24 hours and 50 minutes. To devise a workable and feasible scheme to harness these tides for the economical production of uninterrupted power constitutes the essence of tidal power engineering. Tidal range determines the available head of water at the powerhouse and thus governs the amount of power generated. An average range of 18 feet in this area assures the project of enough power head to run its giant turbines. Three years of intensive research and design and the study of some 60 different arrangements of the project have resulted in a plan selected for design that best suits all conditions of the Passamaquoddy site. To avoid time-consuming computations of energy output, this work was done by an electronic digital computer at a considerable saving in cost. Frequent meetings of the engineering board were held to study the reports of its committees, and a final project plan evolved, designed to produce the greatest amount of power from the most economical and efficient plan of construction. Although design and construction of the project will be highly complex, the plan selected for design is basically simple. The project arrangement will simply close a trap that nature herself has largely provided. The project is designed as a two-pool plan, using Passamaquoddy Bay as the high pool and Cobscook Bay as the low pool. A system of tidal dams to close the bays off from the sea and the installation of filling and emptying gates to regulate the flow of water in and out of the pools will ensure continuous but fluctuating power from generating facilities located at Moose Island. This demonstration model was built by the Fisheries Research Board of Canada's Biological Station at St. Andrews, New Brunswick. Although it is not an engineering model, it vividly shows the arrangement of the huge project and how it would function. All the tidal dams are in their proper places in the selected plan, and the tiny plastic emptying and filling gates function to demonstrate the operation of the project. By raising and lowering the block, a tidal cycle can be simulated. With the incoming tide, the filling gates at Letite Passage and Deer Island would be opened to allow the tide to rush into the high pool, and when the tide is high, the gates would close to trap it there, forcing it to flow through the powerhouse on Moose Island into the low pool, which has been emptied at low tide. Therefore, following the normal tidal cycle, emptying and filling of the tidal pools would occur twice every 24 hours and 50 minutes. Although complex to build, the operation of the huge project is relatively simple. The project includes 4 navigation locks to permit access to all ports in the area. Forty filling gates would be constructed in Letite Passage, and the structures would be anchored to the small islets that stretch across the passage like stepping stones. Although the project encompasses an area of 142 square miles, the individual construction sites are comparatively small. Tidal dams will connect the filling gate structures with the mainland and McMaster Island. A series of dams will connect the succession of tiny islets from McMaster Island across Little Letite Passage to Deer Island. This series of dams and filling gates will close the north end of the upper pool. Construction of the entire project would have an immediate economic impact on the surrounding communities by the influx of several thousand workmen and the expenditure of many millions of dollars for construction materials and supplies. Severe weather conditions will be encountered throughout the project, and bad winter storms and high winds may tax the construction crews to the limit. Heavy fogs blanket the area occasionally. Natives claim that this is the place where fogs are manufactured. Weather conditions like these, coupled with the task of constructing nearly 7 miles of dams in the face of reversing tidal velocities up to 10 feet per second and depths up to 300 feet, presents engineering and design problems without precedent. In spite of these difficulties and the delays they may cause, the project is planned for year-round construction and completion in 6 years. The emptying gates for the lower pool are located south of Letite, between Pope and Green Islands in Head Harbor Passage. 70 emptying gates to empty the lower pool would be built here, and dams from each end of the gate structure would connect with Indian Island and Campobello Island to close the north end of the low pool. Due to the wide expanse of the passage, the force of the rapid tidal currents is not evident, but the tidal flow here is equally as great as in other parts of the project area. Varying water depths from 50 to over 260 feet in this area will tax the ingenuity of construction crews in closing the tidal dams in the face of restricted tidal flows at greatly accelerated velocities. A dam extending from West Quoddy Head across Quoddy Roads to Duck Point at the southern tip of Campobello Island would close the south end of the low pool. Perhaps the most concentrated construction activity of the whole tidal project would take place in the Moose Island area. 2 small tidal dams were built in 1935 and connect Moose Island to the mainland. These dams were originally part of the single pool tidal project undertaken by the United States Army Corps of Engineers at that time. The current plan of the International 2-Pool project incorporates these dams in the new design to separate the high pool from the low pool. Although these dams were built nearly 25 years ago, they are in excellent condition today. A modern highway and railroad built along the top of the dams furnish the only highway and rail connections with Eastport and the mainland. Completion of the new tidal project would open the door for the construction of a new highway system along the tops of the new tidal dams and gate structures to connect all the main islands in the area with the Canadian and United States mainlands. A modern inter-island highway system is certain to have beneficial effects on the future economic development of the area. One of the best places to observe these tremendous tides in action is at Dog Island in Western Passage, just north of Eastport. At low tide, the water is like a mill pond, placid and peaceful. But in 2½ hours, it becomes a ripping, boiling mass. From the very moment the tides turn, a noticeable flow is evident. Starting with a small ripple, it rapidly builds up into a powerful flow. When the incoming tide has run about 1 hour and a half, the water surges through the passage so fast that the surface of the water appears to crown as the tide pushes into the upper pool area of Passamaquoddy Bay. 2 deep tidal dams would be constructed in this area, one beginning here at Dog Island and extending across Western Passage to Deer Island on the far shore, and one extending from Deer Island Point to Indian Island. 50 filling gates would be constructed at the southern tip of Deer Island to work in unison with the 40 filling gates in Letite Passage. The 160 filling and emptying gates would be constructed first and opened to help control the tidal flow while the dams are being closed. Some of the most difficult construction problems of the whole project would be encountered in this area. Water depths in Western Passage exceed 300 feet in some areas. Cofferdams to unwater the foundation of filling and emptying gates must withstand pressures far greater than the tidal dams themselves. Most of the tidal dams can be built with conventional land and marine equipment. Although the arrangement of the project utilizes the most favorable bottom areas as foundations for the tidal dams, 2,900 feet of these dams, about 8% of the total length, must be built in areas where the water is 125 to 300 feet deep. Special bottom dump buckets would be used to place the granular core of the dams in these areas. This is the legendary whirlpool called Old Sow. Local fables tell about ships sucked down to Davy Jones' locker by Old Sow, and the natives in small fishing craft give it a wide berth while navigating in and out of the bays. Although it is fascinating to watch, it represents only an additional engineering problem in the plans of the Tidal project. The powerhouse would be 1/2 mile long and would be located in Carrying Place Cove, northwest of Eastport. The forebay would be cut through the narrow isthmus of land on Moose Island. The powerhouse would be constructed between Matthews Island and the shore of Moose Island, with a tidal dam connecting with the shore to close the gap of Carrying Place Cove. The powerhouse would be the outdoor type, containing 30 generating units rated at 10,000 kilowatts each, coupled directly to giant turbines 320 inches in diameter. These turbines, each weighing over 160 tons, would be among the largest in the world. The generators would be protected by weatherproof housings on the powerhouse deck, and 2 large traveling gantry cranes equipped with movable doors would shield the generating units while being serviced. Operation of the powerhouse would be fully automatic. Generating units would be controlled by computer punch cards or tapes based on tidal predictions. Power output would range from a dependable capacity of 95,000 kilowatts to a peak output of 345,000 kilowatts. A modern administration building would adjoin the powerhouse, and suitable landscaping would beautify the site, for tourists would flock here to visit the tidal project. Had the project been in existence in 1957, an estimated 800,000 tourists would have visited the area. "17 million cubic yards of clay must be excavated to form the intake channel of the powerhouse through this narrow neck of land on Moose Island. Construction of the tidal dams would be scheduled to permit direct placement of nearly all material excavated for the powerhouse and gate structures without costly stockpiling and rehandling. Construction of a bridge spanning the intake channel to accommodate highway and rail traffic and relocation of utilities is also included as part of the project. Tidal power must be generated as the tides occur, rather than when the power market requires it. Therefore, an auxiliary power source to firm the output of the tidal project to its maximum dependable capacity is desirable. Several methods of providing this auxiliary power were investigated. One method employs an auxiliary pumped storage plant. By installing generating facilities across the Digdigwash River, which flows into the Passamaquoddy Bay high pool from the north, water can be pumped from the high pool into the storage basin to produce power at times of low tidal plant output. Fresh water inflow from the river would increase power generation. Seawater would be pumped into the storage basin from the high pool by running the generators as motors, using power from the tidal plant when it is not required to meet the load. This storage would then be released at intervals to generate power to firm the fluctuating output of the tidal plant. The best auxiliary power plant, however, was found to be a conventional river hydroelectric plant constructed on the upper St. John River at Rankin Rapids, somewhat similar but much larger than this one at Beechwood, New Brunswick. Because the output of the tidal plant follows the tides as they change from day to day, peak output from the tidal project would occur at times when the demand of the power market is low. The Rankin Rapids plant, with a dependable capacity of 460,000 kilowatts, operated in conjunction with the Passamaquoddy tidal power plant, would be a combined project of great magnitude. The dependable capacity of this combination would be 555,000 kilowatts, and it would generate annually over 3 billion kilowatt hours of energy. Since the advent of hydroelectric power, numerous tidal power sites throughout the world are being investigated. Here in the New World, the surveys reveal that a tidal project can be built to harness the vast tides of the Bay of Fundy. A project that was once a figment of the imagination, a vision in the minds of engineers, can be a reality today. A project that would operate without the need of fuel of any kind, an inexhaustible source of energy to feed the rapid growth of population and industry that is inevitable in the future. The International Passamaquoddy Tidal Power Project, which may one day be the first large-scale tidal project built anywhere in the world, is a project that would stimulate the economies of Maine and New Brunswick and boost the future development of the whole surrounding area. International tidal power, a new source of energy in a time of need.